Hi students, our today's topic of discussion is chemical properties of haloalkanes, that is chemical properties of alkyl halides. We are done with methods of preparation of haloalkane, haloarine, and even we learnt allylic halogenation. Now when we talk of chemical properties of haloalkanes, we mainly refer to three kinds of properties, one of which is the nucleophilic substitution reaction, then the second one is the action of metals on the alkyl halide, and the third one is the elimination reaction. There are three chemical properties of alkyl halides mainly. One is the nucleophilic substitution reaction, second is the action of metals on it, and third is the elimination reaction. Now children, today mainly we'll be discussing nucleophilic substitution reaction. A nucleophilic substitution reaction is that reaction in which, try to learn with me only, nucleophilic substitution reaction is that reaction in which a weak nucleophile is replaced by a stronger nucleophile, or the reactions in which one nucleophile displaces the other nucleophile is called nucleophilic substitution reaction. Obviously, the strong nucleophile will displace the weaker nucleophile. When I say the strong nucleophile will displace the weaker nucleophile, I mean the halide ion. Right now in alkyl halide, the nucleophile is halide ion. The halide ion can be replaced by hydroxide, amino, alkoxide, acyl oxides, and so on. Basically, students, you know, a nucleophile is a species which loves nucleus. And this species, it loves nucleus. It loves nucleus. It loves positive. It loves nucleus. So it loves positive. So it itself is electron rich. So these electron rich species which love the nucleus can be a anion. Anions are electron rich. It can also be a neutral molecule like amine, ammonia, alcohol, ethers, water, phosphine, where in each case the central atom has got a lone pair of electrons. So they are rich, they are electron rich, they can donate the lone pair. In nucleophilic substitution reactions, nucleophilic substitution reaction, nucleophilic substitution reaction, nucleophilic substitution reaction, SN reaction. The stronger nucleophile will displace the weaker nucleophile. Basically, this is what will happen in a nucleophilic substitution reaction. Now, the nucleophile which will be removed, which will leave the molecule, is called the leaving group. And larger the leaving group, faster is the substitution. Larger the leaving group, faster is the substitution. So, among halide ions, the order of reactivity will be I minus, which is the largest halide among the halides to be discussed. Then the bromide. So, iodide is a larger, that is a faster leaving group than bromide, and bromide will leave faster than the chloride. This is the order of reactivity of the halide ions. Obviously, chloride will be faster than fluoride. So this is the order of leaving group nature. Hence, when I want to study chemical properties of alkyl halides, it is very clear a alkyl iodide, Ri, will react faster than the alkyl bromide, and alkyl bromide will react faster than alkyl chloride, and alkyl chloride will react faster than a alkyl fluoride. So this is the leaving group capacity and this is the order of reactivity of alkyl halides. Now before discussing each and every equation or each and every nucleophilic substitution in detail, first what we will do is we'll just have an outline of all types of nucleophilic substitution that an alkyl halide can undergo, and then we will make the equations. Okay, so on the board. Now see, all eyes on the board. Students, here I am taking an alkyl halide. This is an alkyl halide I am taking. Say R dash X. This bond will undergo fission and the halide, which is a nucleophile, will be replaced by another nucleophile. So I will be calling it nucleophilic substitution reaction. Let's see, the various possibilities are: the alkyl halide can react with aqueous KOH or NaOH, or I can treat it with moist Ag2O, that is silver oxide suspended in water, as a result of which the halide ion is replaced by a hydroxide ion and the product is ROH, an alcohol. I can take alkyl halide treated with ammonia, which is alcoholic in nature, at around 423 Kelvin under pressure. As a result, the halide ion is replaced by a amino group. So I get alkyl amine. Similarly, I can treat alkyl halide with KCN, which is alcoholic. Heating is required. The halide ion is replaced by cyanide group. Then alkyl halide will be treated with AgCN, alcoholic, heat, and the halide ion will be replaced by isocyanide group. Similarly, alkyl halide on reaction with sodium alkoxide, alcoholic, heat. The name of this molecule is sodium alkoxide. It's simple. See, sodium hydroxide, sodium alk oxide, sodium hydroxide, sodium alk oxide. So the halide ion gets replaced by the alkoxide group. R and R dash can be same or different. R and R dash can be same or different. This R, if this R is methyl, this R can be methyl. This is methyl, this can also be ethyl. So the R and R dash can be either same or they can also be different. We can carry out the reaction with silver carboxylate, R COO Ag. Again alcoholic medium. Heating is required. Say this is R dash. Just to understand, reaction will take place like this. R dash COO, and the place of Ag will be taken by this R. So the halide is replaced by R dash COO group. That is the acyl oxy group. This is the acyl oxy group. This much is the acyl oxy group. As a result, you get a ester. The alkyl halide can also be treated with KNO2 heat. As a result, we get RONO. That is, the halide group is replaced by nitrite group. Similarly, we can treat alkyl halide with AgNO2. We can treat alkyl halide with AgNO2, where the halide group is replaced by the nitro group. In this reaction, if I do the same reaction with something special I am telling you, which will be there in nitroalkanes topic, which will come later on. If this alkyl halide is treated with this KNO2, but in presence of a reagent like dimethyl formamide, what I said? Dimethyl formamide. We can also see its structure. See, dimethyl formamide, if I want to make, I will look, I'll just tell you. Formamide. This is form. Amide is ONH2. But instead of those two H, if I write Chatri, it becomes dimethyl formamide. So when alkyl halide is treated with KNO2, potassium nitrite, I get alkyl nitrite. But when I treat it in presence of DMF, dimethyl formamide, I get R-NO2. You will see the reason in the mechanism. We get R-NO2. So what we are getting is R-NO2. Now see, we just understand what kind of nucleophilic substitution is taking place. Yeah, just see which way this nucleophilic substitution is taking place. See, in this case, X negative, the halide ion is that is this, yeah, is replaced by hydroxide. Yeah, so now we will not write so much, only to understand in beginning I have written that. We'll just write by X minus by so and so minus. We'll not write the entire thing. Okay. So halide ion, that is X negative, is replaced by OH negative. This case, halide ion is replaced by NH2 negative. This is a weak nucleophile, this is a strong nucleophile. So halide ion by a hydroxide group here, OH minus, here halide ion by NH2 minus. Okay. Now we go to the next type. Here the halide ion is replaced by the cyanide group. Here the halide ion is replaced by the isocyanide group. Here the halide ion is replaced by alkoxide group. These are the stronger nucleophiles. Halide ion is replaced by OCOR, acyl oxide group. Halide ion is replaced by nitrite group. Halide ion is replaced by nitro group. So this is the difference. Halide ion is replaced by nitro group. So is this clear? This is how nucleophilic substitution is taking place. Now the name of this reaction, this one, is hydrolysis. The name of this reaction is hydrolysis. Say I want to carry out the reaction. So what I'll be doing? Just look at the board. Yeah. Say I take ethyl. So here ethyl, say iodide, reacts with KOH, aqueous, heat to give me ethyl, alcohol and Ki. Ethyl alcohol and Ki. Correct? In this category, same way, ethyl, iodide reacts with NH3, alcoholic, heat to give me ethyl, amine and HI. Right? This way you can go on making the equations. See how I am making. Ethyl iodide plus KCN, alcoholic, heat, I will get ethyl cyanide plus Ki. Correct? Similarly, I come to this category. Ethyl iodide treated with AgCN, alcoholic, heat, I get ethyl isocyanide AgX, that is AgI, heavy metal settle. Right? Then this one, suppose I take ethyl iodide and in this I take NaO3, that is sodium methoxide. Heat. Here we can take methyl alcohol and sodium to prepare sodium methoxide. So I get ethyl, methyl, ether and NaI. Ethyl, methyl, ether and NaI. This one. Suppose I take methyl iodide and I treat it with silver acetate, heat, alcoholic, then I get methyl acetate and AgI, heavy metal settle. Okay, now the next category, say I take methyl iodide treated with KONO. So heat, I get methyl nitrite plus Ki. Methyl nitrite plus Ki. This is Ki. If you can't see, just write it closer. Ki. Okay. Now this one, methyl iodide, Ki, methyl iodide plus AgNO2 will give nitromethane plus Agi, heavy metal sector. So this is how C reactions are taking place. Now one thing which we will do, you may find it difficult to write the equations directly. I'll just write this AgI below as you cannot see it on the screen. AgI. So this is how the reaction takes place. Now, one important thing over here, I'm just telling you the name of all the products which we are getting because you may get confused maybe. So I'm just writing the names. This is an alcohol or the alkanol. This is an alkylamine. So you can just, depending on the number of carbons, you can write the word alkyl. The alkyl cyanide or the alkane nitride. The alkyl isocyanide or the alkyl carbylamine, also called alkyl carbylamine, alkyl isonitrile. This is an ether. It's a ether. This is an ester. That is the alkyl carboxylates. This is alkyl. Take the spelling carefully here. Alkyl nitrite. Te, nitrite. This is a nitro alkane. This is a nitroalkane. So these are some of the nucleophilic substitution reactions. We have not completed entire. There's still more nucleophilic substitution reactions to be done, which I'll just continue right now. In few minutes, we'll go to further nucleophilic substitution reactions. I hope these reactions are clear to you. Now, I'm just repeating it once. Be very, very attentive now. See, we are into chemical properties of alkyl halides. That is, we are into the chemical properties of haloalkanes. Now, in the chemical properties of haloalkanes, the property which we are learning right now is nucleophilic substitution, where a weak nucleophile will be replaced by a stronger nucleophile, or I can say the strong nucleophile will displace the weak nucleophile. The substrate is alkyl halide, that is haloalkane. The nucleophile of the substrate which will be removed is the halide ion. This halide ion is a weak nucleophile which will be replaced by a stronger nucleophile. The larger is this halide ion, the faster will be the substitution. So the order of reactivity is iodide greater than bromide, greater than chloride, greater than fluoride. Iodide will be displaced fastest. And order of reactivity of alkyl halides is alkyl iodide greater than alkyl bromide, greater than alkyl chloride, greater than alkyl fluoride. Now children, some of the nucleophilic substitution which I wrote was, the first one is action of aqueous KOH, or we can use aqueous sodium hydroxide, NaOH, aqueous potash, or caustic soda, or I can use silver oxide suspended in water, which is moist Ag2O. As a result, the halide ion, you can see, is replaced by a hydroxide ion, and we are getting an alcohol. So here is an example where iodoethane reacts with KOH, ye gaya, and you get ethanol and Ki. Next is with ammonia, where a halide ion is replaced by NH2 minus, and see, this one I goes from here and from here one H goes, so we get HI as the byproduct, and the product is ethanamine. Similarly, when I treat with KCN, alcoholic, and I heat, The halide ion is replaced by cyanide and I get a ethyl cyanide, you can see, and this is the byproduct. But now here you have to take care. But when I treat same alkyl halide with AgCN, then this doesn't go. But the ethyl group attacks the lone pair on the nitrogen and gives me ethyl. It attacks nitrogen. Ethyl attacks nitrogen. So I get ethyl isocyanide. This happens because this Kc bond is ionic bond, and this ionic bond undergoes fission in the polar solvent, that is alcohol, and since it breaks, cyanide is produced and the ethyl attacks the cyanide. But children, in case of AgCN, AgC, Ag bond C, that bond is a covalent bond which does not break in the polar solvent alcohol, and the ethyl group, which on fission, when the Ci bond breaks, ethyl does not get any electron of the bonded pair. So, ethyl is electron deficient, but it does not get any electron of the bonded pair. And here AgC doesn't break. So, ethyl attacks the lone pair on nitrogen to give ethyl isocyanide. Now, similarly, when an alkyl halide is treated with sodium alkoxide, I get ether, where halide is replaced by alkoxide, and again this goes. Similarly, when an alkyl halide is treated with silver carboxylate, I get a ester, where, see, this goes. This, AgI, that is the byproduct. Here there is a twist, little bit of twist. What is the twist? When an alkyl halide is treated with potassium nitrite, you get an alkyl nitrite where halide is simply replaced by the nitrite group, and this goes. But when the same alkyl halide is treated with same potassium nitrite but in presence of dimethyl formamide, then I'm getting nitroalkane. And when alkyl halide is treated with silver nitrite, again this alkyl group attacks nitrogen lone pair and you get nitroalkane. Here we are getting nitromethane. Same, this is covalent in nature, this is ionic in nature. So this undergoes fission, but this bond does not undergo fission. So my dear students, I hope the nucleophilic substitution, till wherever I have done, not completed it, not completed the nucleophilic substitution of alkyl halide, still or go. But till whatever number of reactions I have done, I hope it's clear to you. You stay blessed, and love and blessings to all of you. We continue in a short while.